Let's explore matrix multiplication and determine whether the multiplication of matrices is commutative. Matrix multiplication is much more complicated than matrix addition is. Let's take a look at an example to figure out how to multiply matrices. Matrix A is -3, 7, 4, -1. And matrix B is 2, 0, -5, -4. In order to multiply these matrices together, I need to look at the first row of matrix A and the first column of matrix B. To get my result, I take -3 times 2, which is -6, and I add it to 7 times -5, which is -35. So in order to get the entry that's in the first row and first column of my result matrix, I literally need to take the first row and the first column of the two matrices that I'm multiplying together and multiply the two entries and add them up. Next, if I want to find the entry in the first row second column of my result, I need to take the first row of matrix A and the second column of matrix B and do the same process. -3 times 0 is 0, plus 7 times -4 is -28. Now we're moving on to the second row. So if I want to find the entry in the second row first column, I need to take the second row of matrix A times the first column of matrix B. 4 times 2 is 8. -1 times -5 is 5. And finally, to get my last entry, which is in the second row, second column, I need to take the second row of matrix A and multiply it by the second column of matrix B. I get 4 times 0 is 0. -1 times -4 is 4. So to get my result, I just need to simplify each entry. -6 plus -35 is -41. 0 plus -28 is -28. 8 plus 5 is 13, and 0 plus 4 is 4. Now let's try multiplying them in a different order. Let's multiply matrix B times matrix A and see if we get the same result. Matrix B was 2, 0, -5, -4. And matrix A was -3, 7, 4, -1. Our process is going to be exactly the same. First row times first column gives me the entry in the first row and first column of my result. So I get -6 plus 0. Then to get the entry in the first row second column, I multiply the first row of matrix B times the second column of matrix A. 2 times 7 is 14. 0 times -1 is 0. Then moving on to the second row, I take the second row of matrix B times the first column of matrix A, and I get -5 times -3 is 15. -4 times 4 is -16. And finally, to get my entry in the second row and second column, I take the second row of matrix B times the second column of matrix A. -5 times 7, -35. -4 times -1 is 4. So let's simplify this and see if BA gives us the same result as AB. -6 plus 0 is -6. 14 plus 0 is 14. 15 plus -16 is -1. And -35 plus 4 is -31. If we compare our two results, we see that not only are they not exactly the same, but actually not even one entry in either of those matrices turns out to be the same. So the answer to our question is definitely no. Matrix multiplication is not commutative. This might be surprising to you because regular multiplication is commutative, and we saw in an earlier video that matrix addition was commutative, but this is a really important property of matrices. Matrix multiplication is not commutative. So be really careful whenever you're asked to multiply A times B. Make sure that you really do follow that order, because if you multiply A first and B second, you'll get a completely different result than if you multiply B first and A second. Another thing that I want to explore while we're on the topic of matrix multiplication is the dimensions that need to exist in both matrices in order to multiply matrices. We saw earlier that in order to add matrices, the dimensions needed to be the same, but in order to multiply matrices, that's not exactly the case. If I wanted to multiply matrix B times matrix C, I would have 2, 0, negative 5, negative 4, times 1, 2, 3, negative 5, negative 7, 1. Well, the dimensions of matrix B are 2 by 2, 2 rows and 2 columns. The dimensions of matrix C are 2 by 3, 2 rows and 3 columns. If we tried to go ahead and multiply them, and we multiplied our first row by our first column, we would see that we would have enough entries to line up, and so this matrix multiplication would be able to work. The thing to look for is to make sure that the number of columns in your first matrix matches up with the number of rows in your second matrix. The result of your matrix multiplication is going to give you a 2 by 3 matrix. But in order to be allowed to multiply them, these entries right here, columns of the first matrix, rows of the second matrix, need to match up. So now that we know that matrix multiplication is not commutative, we know that multiplying B times C would give us a different result than multiplying C times B. But in this case, it's drastically different. Let's take a look at what happens. I'm going to write out C first, and then matrix B. We determined that matrix C was a 2 by 3 matrix, and that matrix B was a 2 by 2 matrix. And if you look at what I showed you in the last example, the number of columns in the first matrix does not match up with the number of rows in the second matrix. I'm going to highlight what would happen if we tried to multiply the first row of C by the first column in B. And you would see that the entries wouldn't match up. We would have 1 times 2 plus 3 times negative 5, and then all of a sudden we would run out of an entry to multiply by negative 7. So this is just another example that shows that matrix multiplication is definitely not commutative, because BC is possible, but CB is not possible. Finally, I have one last interesting thing to show you about matrix multiplication and whether or not it's commutative. Let's take a look at DE and quickly multiply those together. We should be experts now at matrix multiplication, so we know that in order to get the first entry, we need to multiply the first row by the first column. Well, this time I'm not going to write out all the steps. I would get negative 9 plus 10, which is 1. Then I would need to multiply the first row by the second column. And I would get 3 times 2 is 6, 2 times negative 3 is negative 6, 6 plus negative 6 is 0. Then let's move on to second row, first column. I get negative 15 plus 15, which is 0 again. And then finally, second row, second column, I get 10 plus negative 9, which is 1. The result that I get is something special. This matrix here, 1, 0, 0, 1, is actually called the identity matrix. And as you explore matrices more in later classes, you'll see that the identity matrix is actually a really important matrix. Now I'm going ahead and I'm writing out ED. We know that matrix multiplication is not necessarily commutative, so we don't know that we're going to get the same result when we multiply E times D than we did multiplying D times E. Let's go through our same steps and do first row, first column. We end up with negative 9 plus 10, which is 1. First row, second column, we get negative 6 plus 6, which is 0. Next, let's do second row, first column, and we get 15 plus negative 15, which is 0. And second row, second column, which is 10 plus negative 9, which is 1. This time you see that DE and ED did give us the same result. This only happens in rare cases because there's a special relationship between these two matrices. Not only is this particular matrix multiplication commutative, but the result that we got was something special. We got the identity matrix. So this only happened because because matrix D and matrix E have a special relationship. These matrices are called inverses. So in this special case, our matrix multiplication was commutative, but just to remind you, if we look back at our other examples, matrix multiplication is usually not commutative. In the first example, we were allowed to multiply AB and we were allowed to multiply BA, but we got different results. And in our second example, we were allowed to multiply BC, but we weren't allowed to multiply CB, so the results obviously would have been different. So in conclusion, there are special cases that happen when two matrices are inverses, but in general, matrix multiplication is not commutative.